Do you have any questions on what we've done so far? No questions. Okay, so let me ask my question. If SH max is within this interval, the red interval right here, does it mean we observed drilling-induced tensile fractures or not?
Yes.
Okay, that's correct. So it's above, then it means you observed drilling-induced fractures. If it's below, then you didn't. And that's how we use it to constrain the range of SH max further. And the focus now shifts to hydraulic fracturing to determine S3. Can you determine SH mean from hydraulic fracturing if you are in the reverse faulting regime?
No.
No. What you will determine remains S3, which will be SV in that case. So hydraulic fracturing is the only reliable approach to get SH mean. I'm not going to read this. I already explained all of this in the, I don't know why people keep calling me randomly. I already explained all of that in the video. And so I want to get straight into the leak-off test. So, you know, there are so many related terms, each one being slightly different from the other, right? There's extended leak-off test, there's leak-off test, there's mini-frac, there's micro-frac, there is DFIT, diagnostic fracture initiation test. And of all those terms, only two mean the same thing, which is mini-frac and DFIT, right? Micro-frac is different from mini-frac, as I explained here. Micro-frac and mini-frac are typically done through casing and cement, and they can be done at multiple different depths so that you can get S3 at different depths as you go down the well. But for the leak-off test and the extended leak-off test, you will drill further down into the formation. So you're looking at an open hole completion. Then you begin to pump fluid systematically. And that's why the first part of the plot, which you will see on the next slide, is called a limit test or what? The straight line portion of the test. Here. Limit test or what?
The integrity test?
Formation integrity test. So because the borehole, the volume that the fluid sees when you inject the fluid, right, in here is pretty much constant. But you see that volume is in hydraulic communication with the reservoir. That's why it's your formation integrity test, right? As long as you continue to inject fluid into the wellbore, which has a fixed volume, and there is no leak off into the formation, then you're good. The formation is not showing any leak. You also do that actually to test the integrity of the casing and cement to be sure that your fluid isn't leaking into some shallower depth, right? And that could lead to environmental issues. It could lead to contamination of aquifers, freshwater aquifers. So let's go deep into this now. So can you all explain every bit of this test now? So this is your extended leak-off test. It's been run for as long as possible until you see this fracture propagation pressure. And you should be able to do exactly what I'm going to do now, which is to explain all of this. So first part is linear. Why? The volume of the wellbore is fixed. You are injecting at a constant flow rate, right? So the pressure should increase at a constant rate, just from the laws of chemistry, right? So this is constant. The ratio of V1 to V2 is fixed, and that will be related to the ratio of P1 to P2. So the pressure is increasing at a constant rate, just like the flow rate is constant, right? So as long as you don't deviate from that slope, as long as the slope doesn't change, you're doing a limit test. So if you conduct a test and you stop here, it's a limit test or formation integrity test. If you exceed that point, then it becomes a leak-off test. Why? Because that point at which the slope changes is called what?
Leak-off point.
Point. Above that, the slope changes. Why? The fluid, the fact that the slope has reduced, it not only changed, it became smaller. So the rate at which the pressure is building up is now lower than it was before, meaning the fluid is going somewhere, right? The fluid is now seeing a larger volume than the volume of the wellbore. And that larger volume indicates that you have propagated fracture. So the fluid is going into the fracture. The pressure is still building up, but at a lower rate. Then it can get to a point where there is an inflection and it begins to drop. That point is called what?
Formation breakdown pressure.
Yes, and these are the kinds of questions you will see on the quizzes, right? And now it begins to go down. And that's the one that you might wonder, how come we are injecting fluid into the wellbore? We are pumping down the drilling fluid or fracturing fluid, and the pressure is actually going down instead of going up. And what's happening there? It means the rate at which the fluid is going into the fracture is faster than the rate at which we are delivering fluid into the wellbore from the pump. So that's the important, and that's probably the most tricky part out of all of these other ones to explain. So again, the fluid is going faster into the fracture than we are refilling from the pump. So the pressure goes down. And it gets to a point where it could undulate and eventually flatten out. And that pressure is called what? You know, you're... Huh?
Propagation pressure. Fracture propagation.
Fracture, FPP, fracture propagation pressure. And in a perfect world, meaning low viscosity, low flow rates, no tortuous path of the perforation, that fracture propagation pressure will be equal to leak-off pressure. And you see why some people like to stop the test here, right? Once they see the leak-off point, they think that's the S3 and they're done. Well, that will work provided your flow rates are low, the viscosity of the fluid is low. Otherwise, they will not line up. And that's why we always recommend to go extended, meaning run it until you see this fracture propagation pressure. Then when you see the fracture propagation pressure, well, you can stop injecting. So flow rate goes to 0. Then the pressure begins to drop. Then we study how the pressure drops with time. And at some point, the slope will change. There will be a steeply dipping part, then the slope changes. That pressure at which the slope changes is the initial shortened pressure. Then, and that's you will get by plotting the pressure against time, which you will see on the next slide. Then we focus on the fracture closure pressure, which is this latter part. And for that, you will need to plot pressure against square root of time. And you will see a change in slope, and that will be the fracture closure pressure. And that will give you a reliable estimate of S3, even when you have high flow rates, high viscosity. And that's the moral of the story in extended leak-off test. And the more common term you hear all over the place now is DFIT. And it's no different than your extended leak-off test, which we just explained. So this is what we do to figure out S3 in normal faulting regime and in strike slip faulting regime. That will precisely be SH mean. And we would have obtained SV from the bulk density of the rock mass and the fluids in it, as you did in homework 1. Then you're only left with SH max, and you will now constrain SH max using the stress polygon, since SH max is a function of SH mean in the stress polygon. And all that I've explained, I documented in these couple slides, so you can read, and guarantee there will be questions on this in the quizzes and probably in the finals. Any questions on that? Oh, this is an example. Actually, 2 examples of leak-off test on the same well. One was shorter than the other. Did anyone calculate this time interval in days? This is minutes. 60 minus, let's just assume it's 15. 60 minus 50, 45 minutes. So it's actually very fast. So in 45 minutes, you're already here and you're done. And this would have been a good test if the viscosity is low and the flow rates are low, because all you need to do is to draw a straight line here, and that leak-off point will give you S3 and you're done. But if that's not the case, then you need more data, right? So this one doesn't show any fracture propagation pressure. There's no horizontal part here, right? So the 45 minutes is not long enough to do an extended leak-off test on this well. So they did a second one, and now you can see the horizontal part. So that's a fracture propagation. So this is an extended leak-off test. This one will just be a regular leak-off test. And then you can analyze these parts for initial shortening pressure and fracture closure pressure. And this one was how long? I'm just going to assume this is 70. This is precisely 70. This is 65. Let's assume it's 65. Was 115 minus 65.
$50 minutes.
So this is 50 minutes. This other one was, what did we calculate that to be? 45, I believe. Right, it's at 60 minus, yeah, it's 45 minutes. So 5 minutes changes everything, right?
So 5 minutes can be an appropriate difference between being extended or a standard leak-off?
Yes. So all you lose is 5 minutes. It's well worth it, especially if you know your pumping rates are high and the viscosity is high, or you have some complex perforations in there that could make the path of the fluid to the fracture thoughtwards. So the point is, don't be in a hurry, and that's the message for the service companies. If you're an engineer and they want to do it very quickly, like, yeah, we've seen a change in slope, you're done. Yeah, you're not really done. You want to wait until you can see the horizontal part, and it might just mean waiting 5 minutes. So the lesson here is go until you see your horizontal part and the pressure. And this data shows up live, right? They stream it live. So you can actually wait until you see it, then you say, okay, now you can shorten it and you can grab the rest of the data. And that duration can vary depending on the rock properties of the formation you're doing the test on. And this is the data from the first, all right, and from the second. From the first, we know the result is not going to be really very reliable because we never really saw the horizontal part, unless you want to believe that this is a horizontal line, which is not necessarily reasonable, right? You want to wait until you can actually see it clearly, until there is no ambiguity in your identification of the fracture propagation pressure. So you can interpret it still, except that the results will not be the same as that here. And I already read out those values in the video. So I'm not going to do that again, but you can see a change in slope here. So that's your initial shorting pressure. You can see a change in slope here. That's your initial shorting pressure. And they're slightly different. And you may think, oh, it's almost 50 psi different. Well, what's 50 psi over 2000 in percentage is negligible. So that accuracy is actually good. So that's why we say hydraulic fracturing, meaning all these tests, extended Likov test, defeats, is a reliable way of estimating S3. The accuracy is good.
I had a quick question about this. So if we do one leak-off test and then immediately do another one after, won't we get some like weird estimates for what the S3 would be since you already fractured the formation?
As long as you propagate the fractures longer into the, so let's assume you have a well here and you created the fracture this long and you did your test. If you go back there and you repeat the test again, it's going to behave like the previous one again, but you will have to continue injecting until you get until you propagate the fracture deeper into the formation. To propagate the fracture deeper into the formation, yeah, then you have to incur the fracture propagation pressure again, right? So you will have to overcome S3. So you can use it to get S3 again. And the results will not be very different from the previous one. And if they had done this a little longer, that's what you would have had. So you're still able to repeat it a second time because it's now a bigger volume, right? The pressure will build again, and you can still see initial shorting pressure and all the other parts, only because you have propagated the fracture longer. To propagate the fracture deeper into the formation, well, you're going to have to overcome S3 a second time. Good question. And the other point is, what type of pressure is this? Can we conclude that this is your S3, that your S3 is 1925 psi? Okay, so what's your S3 going to be?
You'd have to add the hydrostatic pressure or the mud pressure from the column.
Correct. You have to add precisely the mud pressure, not the hydrostatic, right? Unless the pressure of unless you have water in the well. If you have any more viscous substance like your mud, well, is the weight of the hydraulic column. And you will add that to this to get your S3, because this is surface pressure. But S3, your stresses are absolute values. They are not surface values. And that was for ISIP, initial shorting pressure. This is for FCP. So it's against the square root of time. Again, previous one, it's against time. For fracture closure pressure, you plot it against square root of time. That's when you'll be able to see the change in slope. And you can get your fracture closure pressure at that point where the slope changes. And again, they're slightly different, obviously, because you didn't run this one till you saw FPP, fracture propagation pressure. So this is the correct one. But even the differences are small. When you convert it to percentage, it's negligible because you're looking at large values of bottom hole pressure or large values of stresses. And these results will only work when, I mean, this result, this good one, is robust. It will work even when you have high rates and high viscosities. But the one from the first one that didn't really see a clear-cut fracture propagation pressure will only work when you have low rates and low viscosities. I keep mentioning that. Any questions before we move on to?
I had one quick one again. I guess why would your fracture closure pressure be different for those two? Because you're still creating the fracture since you saw the deviation from the linear slope in the first one. Shouldn't the closure pressure be the same if you're still creating a fracture? It doesn't really matter if you've gotten to the flow rate that where fluid going out is more than fluid going in.
I think this one is questionable still, because remember, if you don't see this, what does it mean? It means the last thing you saw, you're hoping you saw the fracture breakdown pressure, right? That's what you're assuming. You saw the breakdown pressure, and like we discussed, and after that peak, what's happening here? Fluid is traveling faster into the formation, right, than into the well bore. Then you shut in the well immediately. You shut in the well while this is going down. So you don't really know for sure whether this change in slope is coming due to the shutting, or is coming because of the drop in pressure coming from right after fracture breakdown pressure. You never waited for the rate of the fluid going into the fracture to balance out with the rate of the fluid going into the well bore. So all of those dynamics are going on here, and you're trying to interpret it as closure pressure or initial shutting pressure. So that's why it's questionable. So you really need to wait until it comes down and settles, and you see that horizontal line. Now you're sure that it's not like, you're sure that the rate of the fluid going into the well bore has balanced out that with the fluid getting into the fracture. So there is no change in slope. There's no drop in slope due to that. And on everything you see, I mean, the loss of pressure is entirely because we shut in the well. So that's what the second test does for us. Whereas the first one doesn't, because it's ambiguous. The interpretation of the results and that interval will be ambiguous unless you actually waited. Good question. Any other question before we move on? This thing is too big. Good. So now we move on to failure analysis in a vertical well. Crush equation, right, for vertical wells. This is the one we've done before. And I explained all of this, so I won't talk much about it. There was a minus here trying to account for the fact that you put a positive value here, then you need to put minus here for tensile stress, because compressive stresses are positive. Pressure is also compressive, so it's already set up properly. But I said the minus is irrelevant because we're going to assume the tensile strength is 0 because rocks are extremely weak in tension. And we already saw this equation. All you need to do is to figure out the angle, the theta, at which tensile fractures form, which is theta equals 0, right? In the direction of SH max, because theta is measured relative to SH max. So that's where you have the least compression, and that's where drilling-induced tensile fractures get initiated. So theta goes out of this equation for drilling-induced tensile fractures, and obviously we've had to assume R, which is distance from the center of the well to any point in the reservoir, is equal to the well bore radius. So those are the two substitutions that have been made to the general form of the Kirsch equation. And we got this. Then we set that minimum equal to 0, because that's when the rock goes into tension and you create the drilling-induced tensile fracture. So how do we constrain I mean, I showed it graphically how to draw the drilling induced tensile fractures, right? I showed it and said you'll be above if you observe drilling induced tensile fractures. Well, the way you do it is just make SH max the subject of the equation right here. So take SH max to the other side, and this is what you get. And now you see that you can have all of these values, right? And basically SH max is a function of SH mean. So how do you plot it? And that's what you're going to do in homework 4. All you need to do is give reasonable values, a range of values for SH mean, right? You already have the polygon, so you know the range. Let's assume this is the polygon. That's a poor sketch. But you already have a range of SH mean in the polygon, in the stress polygon, right? Keeps refreshing. It's from here to this point. So you can put a table of say 10 values starting from here and ending here, right? Starting from the smallest, let's say 100, and you go to the largest, say 1,000, and you can increment, or let's even make it start from whatever. It's not really important. Let's make this 5,000. So we can go in increments of 500. So the first one is 500, then 1,000, 1,500. You come up with that for SH mean. Then use this equation to get the corresponding SH max, because all that is left to come up with SH max is SH mean. And now you've come up with your table for SH mean. So at different values of SH mean, you can calculate SH max. This negligible, delta P is P mod minus pore pressure. This is pore pressure, and you will be given those, or you make an assumption. And now you have the equation for a straight line, right? And you can plot this against that, and you get the straight line. That's what you'll be doing in homework 4. And I already explained this. So how about well bore breakout? That's what we haven't done yet. So that will be the same equation, but not at theta equals 0, which is when you form drilling induced tensile fractures. This will be when theta equals 90 roughly, right? That was if there is no breakout. And so we introduce the concept of the width of the breakout, which is this angle. So in this nomenclature is width of breakout, WBO, when you're working in radians. And it's phi b when you're working in degrees. And I explained all of that in the video. And you can already see half of that width is this, right? When you add it to this, it has to be 90 degrees, right? And that's how we came up with this equation. I explained that in the video. And for this, same deal, but we do it for 180 degrees. So theta b plus WBO plus theta b will give you 180, and 180 is pi radians. So 2 of theta b plus pi, no, equals pi, right? 2 theta b plus W breakout, all right? Now it's looking too rough. 2 of theta b plus the width of the breakout equals pi, which is 180 degrees, right? This theta b plus this theta b, 2 theta b plus the width of the breakout, which is measured in radians, gives you this. So make this the subject of the equation. It becomes pi minus WBO. So we have now replaced theta by theta b, because you can have a breakout with a finite width. So previously it was just theta in the cross equation, now it's theta b, and you know how theta b is defined. Again, you've already assumed R equals big R. And that's the equation for crush. That's your crush equation for hoop stress. And we know that we're going to create breakouts when that hoop stress exceeds the compressive strength of the rock, which is C effective. So typically it's going to be less than or equal to that. When it equals that, then you induce breakout. So this equation is for the initiation of well bore breakout. It doesn't describe what happens after the breakout is initiated. That's the important point. And again, we can make SH max, which shows up here, the subject of the equation. And what you get is the second equation right here. So you'll be given the rock strength, or pressure, all of this like before, the width of the breakout. And the only thing you need to find, the only unknown is SH mean. So you're back to the same idea here. SH max is a function of SH mean. So you do the same thing by using a different equation, right? Provide the same interval or whatever interval you want and calculate SH max according to this equation. And you get another line. And that other line, well, before we go to the other line, quick point on width of breakout. If this is the center, you see that the angle, breakout angle, written as WBO, is fixed as the fracture, as the formation around the well bore gets crushed. It goes deeper and deeper into the formation, but it doesn't go wider. And that's good for drilling. So this is some pictures of how it looks like in reality. It used to be like this. At this point, this part is just giving way. And after multiple episodes, you get down here. The width never changed. And that makes it safe to drill this well successfully. But if the width was so large, greater than 90 degrees, you will see that the entire hole will widen and you will have stock pipes, you have drilling problems. And I explained all of that in the video. But now, these are, what lines are these? Drilling induced tensile fractures for well bore breakouts.
Well bore breakout, right?
Yes, because the drilling induced tensile fractures, remember, the equation for drilling induced tensile fractures is very similar to the equations for strike slip faulting, and they tend to be parallel to that. So when you see a line that is almost parallel or close to the strike slip faulting, is drilling induced tensile fracture. When it's at a different angle, then it's the well bore breakout. But you don't need to memorize that, right? Because you are the one who will calculate this line. So you will know the equation you used to come up with this line. If you use the equation for drilling induced tensile fracture, yeah, then you know what the line is, right? So that's what you're going to do in the homework. You first come up with the polygon, then you constrain it further with data coming from a Likov test. And these are the different rock strengths that were used at this point, right? Remember, it's a function of CF, C effective, which is the rock strength. And again, it's C effective is the rock strength in the reservoir. Is it the same thing as UCS? No. And I don't remember if we addressed that problem in the definition of your homework. I think your homework was set up so that we don't care. We just use it like it's rocks. We just use it like it's rock strength. We use UCS like it's rock strength. But I'll look at it before I upload it and probably just change it to C effective. So in the real world, the service companies or however you get the data, they're not trying to help you, or they should try to help you, but you can get data where what you are given is UCS. Does it mean you use UCS as C effective? No, it means you're going to go come up with your Morse circle, right? You do your Morse circle plot. You figure out what value they gave you, right? So if they gave you C, or better still, they gave you UCS, right? But you have already done Likov test, or they gave you data for Likov test. So from that data for Likov test, you know S3. So you draw the line, you can assume that slope, right? Or even do two slopes, one at the 0.6 and the other one at 1. So you cover the whole range, right? Then you draw the smallest circle you can draw, starting with this at 0. So this is your UCS that they gave you. And you already have the line that intersected that UCS. So what you will do is to figure out where your S3 is coming from your leak-off, right? They gave you data for leak-off. Then draw the largest circle you can draw that will just touch the failure line, right? And this point, even though it hasn't displayed it yet, this point will be the C effective, right? That's the value of the strength of the rock. So you'll just have to use the concept of more failure envelope to get you the data you want. Then use that in your equation. Is that clear? And to come up with this line, this was the assumption. The well-bore breakout angle or phi BO is 45 degrees. And now if you observe, if the rock strength is 110 and you observe well-bore breakout, then you will be above, just like in the case of drilling-induced tensile fractures. If you don't observe it, then you will be below that line. Is that clear? And I like to ask those kinds of questions even in finals. And I can say you observed it or you didn't observe it. So you have to really understand when to go above the line and when to go below the line. And all of this you can read. And these parts, I explained it in the videos. I wanted to watch the videos. I wanted to give you a complete picture. Like I mentioned in the videos, these are typically done using computer software packages. It's mostly geometric calculations. You're just rotating stresses. Cross equations don't work anymore because your well-bore is inclined. And the software packages will give you results that look like this at different depths, and you can interpret these and figure out the best direction to drill your well, or to drill through difficult zones. So I back up to this. This is the standard breakout in your vertical well, is corresponding to this portion of the well. Then the well is deviated now, and it's now on the sides, but at an angle. And this is the circle I showed earlier, and it's like projecting where your well will be, the direction of your well on the lower hemisphere, pretty much like we did with StereoNet. So vertical wells will be right in the middle. Wells deviate, completely horizontal well. If the well is completely horizontal at that depth, it's going to lie on the circumference of the circle, right? So there are 3 lines here. So if the well is deviated at 30 degrees, you'll be here. You'll be on this circle. If it's deviated at 60 degrees, you'll be here. Then what about where you are in this direction? That's precisely your azimuth. Well, azimuth. So is it drilled this way or that way? Yeah, on top of the angle. So that gives it the direction. And those two completely define the orientation of your wellbore. And again, the far field stresses will get reoriented along the wellbore. So now the wellbore is deviated. So there's some geometrical calculations on how to rotate it. And again, the cross equations don't work anymore. You have to plug in that angle and orientation into a tool that's going to do the geometrical calculations, which we wouldn't be talking about here. I already discussed rotating stresses and all of that and gave you a code for that. in module 1. It's pretty much what they do. But on top of that, they solve the numerical problem for the concentration of the stresses. The other point is what drilling fractures look like. I mean, drilling-induced tensile fractures, what they look like when your well is deviated like this. They still look almost vertical, right? And again, they're still localized, so they don't go very far away from the well bore. And so because they're looking almost vertical, when you actually look at the borehole image, then they appear as an angle, right? Because this direction is aligned with the inclination of the well. So these guys that were vertical now are at an angle, and that's the Nechelon form that was mentioned in the slides, which I'll let you review here. That's what they appear as. So when you see those lines, like so, you see them here? Those are your drilling-induced tensile fractures. And again, like in the vertical well, you don't want to confuse them with your natural fractures, right? And I explained all of these. Any questions before I go into this? Because this basically takes us to the end of the module. Any questions at this point? No? Okay, so like I said, this is using the software package. These are the inputs for these different Anderson's faulting regimes. And this is the required UCS. So they've done the calculation at the rock strength, at the prevailing conditions of stresses in situ, and figured out what the corresponding UCS is, right? Meaning you worked with this the other way. So you figured out this was your stresses in the reservoir, your least and maximum. Then you work backwards. This was the rock strength, right? And this is the least principal stress. Then you draw the smallest circle you can draw that touches 0. And that would be UCS. And that's the required UCS, right? To create what just happened. Good. That's the required UCS. That's the required UCS to initiate well bore breakout. Again, initiation, not propagation of the breakout into the formation like we saw earlier, right? So if it's very high, you need the rock will have to be very strong in order not to create breakouts at 45 degrees. I believe this was set up at 45 degrees. But if you're here in the blue region, then the rock doesn't have to be as strong. It just needs to be about 75 megapascals. It needs to have a UCS of about 75 megapascals before you can induce well bore breakout. So if you don't want to have lots of breakouts or you want to avoid breakouts, you will want to drill a well at an angle of about 70 degrees, a well that's deviated at about 70 degrees and in this azimuth, right? North, west, 10 degrees, roughly. Or south, east, or north, east, whatever this angle is, right? So that's how we use this stuff. So when they're trying to drill some extended reach wells through like difficult shales, pliable shales, they'll figure out which orientation you can drill through that will give you the most stable well using the software packages. So that's the whole purpose of all of this. And it's going to apply to whatever faulting regime you have. And you see they are different, right? So here you want to drill in this direction. Here you want to drill in this direction to minimize well bore breakouts. And for drilling-induced tensile fractures, they actually swap this. So the high is actually the blue, and that's the required mod weight. So if you want to be able to, if you don't want to easily form drilling-induced tensile fractures, then you want to drill in this direction, because your mod weight only needs to be about 32 megapascals, which is precisely the pore pressure. And you wouldn't form drilling-induced tensile fractures. If you want to form a little, then you can go here. You can basically control what to expect using this information. And you can do that regardless of your faulting regime, because these things are calculated and they are also calculated at different depths. So don't assume this will be the same as you go down, right? Any other questions before we wrap it up? Okay, 3 more slides. I just want to mention the fact that for the well bore breakout is initiation, and it doesn't account for how it propagates using this image, because I've shown that before. So this is propagation of the well bore breakout into the formation. Those equations don't tell you that. They tell you when this guy begins to go in. That's all. But I also want to point out, while in this image, that as this is breaking, right, this is creating more cuttings that go into the hole, and you will need to circulate out. So if you have lots of breakouts, you have lots of cuttings, yeah, it can affect the hydraulics, right? And it can cause drilling problems. If you have too many cuttings, it can cause stock pipes. And those are the issues you want to avoid. And we'll be talking about that here. So importance of well bore stability. And I'm not going to go into all of this because I already spent time on this in the videos. Important thing is well bore stability costs you money. So mechanical earth modeling will give you enough data to assess the stresses vis-a-vis the rock strength, because that's all that drives all of this process, right? It's always stress magnitudes vis-a-vis rock strength. And we already know there are different types of rock strength, right? There is the compressive rock strength, which when your compressive stresses exceed that, you form breakouts. And there is the tensile rock strength. When the minimum hoop stress goes below that, you form drilling-induced tensile fractures. And these are precisely mechanical earth modeling components, MEM components, which we talked about at the beginning of the course. So using mechanical earth models, you get these parameters, and you can use these parameters in coupled geomechanics and flow simulation, which we discussed in module 3, right? Temporal elasticity. Remember those equations, del dot sigma plus body forces equals 0, which is your KU equals F that you solved in your finite element class. That's the equation governing your geomechanics. Your material properties will go into K, elastic moduli, right? And using geomechanics coupled with mechanical earth modeling, you will be able to predict when you're going to have breakouts and when you can have sanding issues, formation damage. All of these you can predict and avoid it. You can find the orientation, the well bore inclination that is going to minimize the drilling risks and prevent or curtail the amount you end up losing to well bore stability issues. You can actually lose your well, right? Even when the well has been drilled already and is producing, if you have severe stresses build up, pore pressures go down, right? Effective stresses increase, and these are compressive. If those stresses exceed the strength of your casing and cement, your well bore collapses, the money you should have made from the well you lose, then you also need to spend a lot of money to plug in the well so that the well doesn't flow into some shallower aquifers, which could be sources of drinking water. So this is a very important slide. Watch it in the video. And how do you prevent wellbore instabilities? A key is by controlling the width of the failure zone. I said it's typically less than 90 degrees, like seen here. So as long as it's less than 90, you can go deeper into the formation, the width doesn't really increase. But if it's more than 90, then as it's going deeper into the formation, this is also going down into the formation, it can easily lead to washouts, which can cause your wellbore to collapse, right? Because there's nothing holding your wellbore anymore. That material gave way. And actually, we don't just aim for 90 degrees. We try to keep wellbore breakouts less than 30 degrees in practice. So we generated those figures again for wellbore breakouts, but now using wellbore breakout width of 30 degrees. And this is what you get. So if you drill in this direction with this mud pressure, you are expected to have a breakout of about, wellbore breakout of about 30 degrees, which is manageable. So that's how you use this stuff. If you want to get less breakouts, well, increase the pressure more, right? So PMOD will be greater than 31. If you make P1, say 32, you wouldn't see any wellbore breakouts, provided all the input parameters in your model matches reality exactly, right? Because there will be uncertainty in estimation of rock strength and all those other parameters, for instance. And you have the results for the different faulting regimes. And the application of this stuff in many real life cases where they had to come up with intelligent angles so that they can avoid wellbore problems. You will see those examples in the book in chapter 10 and also in the online reservoir geomechanics course, where the service companies have tried multiple wells, like 2-3 wells, and they lost all those wells. Then they talked to the professors working in this area, and they used their software to design an orientation, and they went through and drilled in that orientation, and they were able to drill the well successfully. So this technology actually works in practice. And that's pretty much it. Any questions? No questions. Okay, so this concludes module 5, and we'll move on to module 6 next week, unless we get this software. We are close. They sent something, but I didn't see the license in there, or the IT guys didn't see the license in there. So we're very close to getting Abacus, which is the last piece of the last piece required to do the labs. So definitely, I'm still chasing that, and I hope we get that before next class. Other than that, prepare for your quiz. Definitely, we're going to have a quiz next week. Today is Tuesday, right? So we have a quiz Thursday. But definitely, we have a quiz Thursday. It's going to start from wherever I stopped in module 5. It's unlikely it's going to be able to cover everything in module 5. So there'll probably be one more quiz on module 5. Then we'll go to module 6. And the course is getting closer and closer to the end. Module 7 more or less covers the big picture. So you're not going to see too many questions on module 7. So module 6 is where you can, module 5 and module 6 is where you can actually raise your score on the quizzes. There won't be more quizzes after module 6, maybe one quiz or something, but yeah, we're almost done. So expect maybe 2 quizzes on module 5 and maybe 2 more on module 6. Where does that take us? That takes us to 12. So maybe I'll have one more on module 7. So we aim for 13. 13 is what I had said before, or we aim for 13, but I can actually do 14. But I've seen that your grades were a little higher than what you had calculated by hand. It's because I implemented the tool that selects best 6. So right now I set it up to drop lowest 2. So it dropped your lowest 2 quizzes and kept the highest 6. But by the end of the semester, I'm going to keep the top 10. So I'll probably do 14 quizzes so you have extra room to make up your grades. And that's pretty much it. Any other questions? Do you have any questions on the finals or the homeworks? Any questions on the homeworks on labs will go to Aaron. But do you have any questions on the finals? Is there any question in the finals? I said finals, midterm. Is there any questions on the midterm that you are not 100% sure of how to solve? If there is, you can always stay back and ask.
I think there was a few things that I still wanted to clear up on it. Just some simple things about the sketching it up and deriving the equations to apply it correctly. Nothing major.
I'll do it right now. And if Jacob, if you don't have any questions and you're not interested in the in the solution, probably because you got those questions, feel free to log out. So I'm going to find it on this computer, so I'll stop sharing it. Actually, this one should take over once I share here. Yes, good. And where are the solutions? I'm not sure if this is a good approach because it's on the other computer. I can sketch, but I'll show the answers first, then I can sketch later. I think that's the wiser way to go about it. Okay, so we're looking for midterm solutions. So basically, this is the question. It's made up of 4 layers. So when I said sketch, actually, this will be 3. Right? And that's easy to see from the fact that I give you 3 parameters. And no one was confused with that. So starting from the topmost layer, so you sketch 1 layer, which will be 1 rectangle, which I can do here easily. I can do over there. But you have 1 layer. Just imagine. This command is not going to work here. I have to. Can I do Control N? Okay, I can do it. So imagine this is layer 1. Layer 1, layer 2, layer 3. Oh, that's layer 2. Let's use some red. All right. So that's your reservoir. It's made up of 3 layers. We blocked it, basically like your blocking, which we had discussed before. So the density of the first layer, 1,000. Second one, 2,500. Third, 3,000. So you can put those values inside those boxes I just colored. The thicknesses. So the first one is 100 meters thick. The second one is 500. So this is 100 meters thick. This one is 500. So I can artificially make it bigger by doing something like this. So it's equivalent to 5. And the last one is what? 1,000. So like 10 cells combined together. 8 to 18. So something like this is what you have. So to go from the top to the bottom is going to be 100